Now I am starting with the MODFLOW basics. Model is a mathematical representation of either physical process. It mathematical representation of physical process is known as a mathematical model. A simplified version of the real world system have here a groundwater system. We are doing about the groundwater system and balance whatever, and that approximately simulates the relevant excitation and response relations of the real world system. What are the objectives of the groundwater modeling? To determine the to study or predict the effect of the changes of the hydraulic head with respect to space and with respect to time, like groundwater. We will be using the groundwater for the pump. For the domestic purpose, industrial purpose, and agriculture purposes mainly in India. We will be using them. So there should be some balance required with the supply and demand, so that we need to study the effect of the hydraulic head inside the aquifer. Hydraulic head for the confined aquifer, water table head for the unconfined aquifers. For understanding, not only for the mass balance things, you can simulate the groundwater quality variations by using the M3 3D MS model in the MODFLOW. Uh, there are three types of the process included in the contaminant transport: advection, dispersion, and diffusion. This is a non-reactive model, this MT3DMS, but there is a reactive model also, that is RT3DMS. But in Morpho, they are studied only about the non-reactive transport models: advection, dispersion, diffusion. Advection means, suppose if there is any contaminant like points source from the industrial source, there might some contaminant has been introduced into the groundwater. Yeah, it has been accidentally released, so that some amount may have been infiltrated and percolated to groundwater table. The groundwater will be having some velocity at very low. With that velocity, the contaminant moves. It is known as advection. Dispersion means, due to the heterogeneities in the aquifer, uh, the contaminant may move the horizontal or the vertical direction due to dispersion or the heterogeneity present in the aquifer. It is known as a dispersion. It is two types: longitudinal dispersion as well as the lateral dispersion. Diffusion means, from the higher concentration region to it will diffuse into to the lower concentration region. That is known as a diffusion. There are types of the groundwater models: empirical models, numerical models, analytical models, and physical models. Empirical models means they derive from the data, statistical data. They develop some equations empirically, and they will determine the groundwater table. There are some machine learning models or artificial intelligence models. Those all are the empirical models. Numerical models, they here we have some physical process equation that we will discretize by using the finite difference, finite volume, finite element method. That is known as a numerical model. Analytical model, by using the Fourier transforms or the Laplace transforms, we will convert the partial differential equation to algebraic equation, and therefore we will solve it. And the physical models, we will downscale the real world scenario. We will downscale the physical world scenario into the lab scale, so that we will simulate the process by using the sandbox model. This is the sandbox model. Types of the modeling applications: predictive, interpretive, and generic. Predictive means, we will simulate the hydraulic. We will determine the hydraulic head, and we will calibrate the model and finally validate the model. After that, we will do the prediction of the hydraulic head for future, uh, see, for future time. Interpretive means, when, yeah, when we are they have to, when there is some contaminant, and we have to map the area with respect to time and with respect to space, how the concentration is varying. Suppose, for example, that is known as interpretive. Generic means, there are some scenarios. Suppose if there is change in K, what will be the change in permeability or the change in the storage, what can be the water table position. I mean, there are different. Suppose you can do a sensitivity analysis for the generic model, like that. I mean, it's just generic. Interpretive and generic not needed. For calibration is not needed, and validation is also not needed. But for the predictive, you have to do compulsory validation and calibration both. Yeah. While coming to the conceptualization model, actually, this conceptualization model is the heart of the groundwater flow model. You can say that. I mean, actually, during the contamination transport also, first of all, you have to develop the conceptualization model, and thereafter groundwater flow model, and thereafter the contaminant transport model you can develop. You cannot develop directly the groundwater transport model. I mean, contaminant transport model. First of all, you should develop the flow model, and thereafter only you can develop the contaminant flow transport model. But here the conceptualization model is nothing but hydrogeological mapping. Hydrogeological mapping is the identification of the future physical boundaries of the aquifer systems and their hydraulic and or the hydrologic characteristics. Here it is focused on mapping the storage and transporting properties of the rocks or the alluvial soils or whatever, and also mapping the stratigraphic units. Hydrogeological mapping is the first step in developing and understanding the aquifer geometry and location. See here, understanding here we have the different boreholes data we have. This we know the latitude longitude of this borehole. We know the latitude longitude. We know the latitude longitude here also. We know the latitude longitude. Yeah, for all this we know the latitude longitude. From the latitude longitude using DEM, you can get the elevation. After that, you will know the elevation of this first layer. Suppose this is the totally the same type of sand layer, something assume that it is sand and orangish clay. uh, from you know the top elevation, and you know the at what depth, up to what depth the sand is present, and you know the up to what depth the clay is present. You can develop the elevation of this layer, elevation of this layer, and elevation of this layer from the top, and you can minus with the top elevation, and you can get the for all these things you can get the elevation of for the different layers. You can get the elevation, and you can do interpolation for each layer by using ArcGIS, and therefore you can develop the somewhat, I mean, to some extent you can develop some layers of the conceptualization model. It is very important step, and it is the heart of the groundwater flow model. We should be very uh, I mean, very much accurate in this conceptualize. If your conceptualization model is wrong, then your total groundwater flow will be wrong. Flow model will be wrong. So you should be very strictly. You should consider this the conceptualization model. I mean, not only this. I mean, hydrogeo and understanding the aquifer geometry and location where the water enters and the water withdraws. That is also the main thing. Not only the storage and transferring, but also the recharge as well as the drainage, discharge or pumping, whatever. This information should be also should be given accurately to the model. Therefore only you can simulate whatever the things you want. Assumptions. So while coming to assumptions of the groundwater flow model, you need to you investigate your aquifer in a good in an accurate model, like conducting the geophysical investigations, conducting the hydrological investigations, lithological investigations. All these investigations you have to do perfectly. If your conceptual model is wrong, then no need, your groundwater flow is absolutely wrong. The kind of the solid matrix comprising the aquifer with reference to its homogeneity and isotropy, heterogeneity, and anisotropy. The mode flow, the mode of the flow, whether it is one dimensional, two dimensional, or three dimensional, flow regime, the properties of the water, the compressibility. I mean, you know that compressibility depends upon the density of the fluid present in the aquifer, and the effect of the dissolved solid is temperature, density, the presence of the assumed shock fluid boundaries. Suppose if there is some seawater intrusion, you have to delineate by using, I mean, you have to collect the samples and you need to delineate the salt water freshwater interface, that boundaries it is saying, and the relevant state variables and the area of variables, the sources and sinks of the water, or initial conditions. When you are, suppose, while coming to initial conditions, suppose if you are running the model from 2010 to 2020, you need to provide the initial water table at 2010. At what particular level the water level is there in your aquifer. After that, you will be providing the recharge, discharge, all these things. Therefore, it can simulate the system. And selecting the appropriate conceptual model for a given is one of the most important steps in the modeling process, as I have said. Actually, this diagram is known as a fence diagram. Fence diagram means it is the mapping the aquifer, different aquifers. I mean, it throughout the even regional space. I mean, you can see the different. This can be made in the arc scene also. ArcGIS, inside that ArcGIS, there is a different type like ArcMap, ArcScene, ArcCatalog, all these things. In ArcScene, you can view it three-dimensional manner. After I mean, this is a discrete. These uh, boreholes are the discrete representation. If you combine the borehole and the geophysics, it will be like a continuous representation. Okay. I mean, when if you have the idea of the geophysical investigation, you can have the you can get a continuous formation of your subsurface. But if you don't know geophysics, it will be like a discrete model. See, they have been interpolated, linear interpolation they have been done. But if you know that geophysics, it will be good for the groundwater investigation, radiological investigation, whatever you want. Yeah, this is about the conceptualization model. While coming to groundwater flow model of the concept, you need to know details about the representative elementary volume. What is this representative? I mean, actually, before coming to representative elementary volume, you need to know the porous media. How the porous media will be, we will assume. Actually, porous media is a continuum that replaces all the real complex system of the solids, voids, and the filled with one or more fluids that comprise the aquifer. I mean, we know the aquifer will be having the solids and the liquids, two phase. But in unsaturated zone we have three phase. But we are only studying the saturated zone. That is the voids filled with the fluid. Inability to model and solve the problems of the water flow and contaminant transport within that void space is due to the I mean, you need to have the minute information data to map the aquifer. But in each and every throughout the space, it is very difficult to get that type of the minute information related to your aquifer. There comes this concept, the representatory elementary volume. It will help to describe your aquifer in a minimum volume. That volume, I mean, the properties of that volume, the storage or transmitting properties of that volume will represent the entire region of your study area. Suppose if this small volume is V1 that you have assumed, suppose if you here there is a maximum porosity. See, this is a hydrogeologic characteristic, this is a volume. Suppose you are considering the porosity as one of the characteristics. Suppose here in V1, if you consider this point, there is more porosity in this point, so it is maximum porosity. When you just move this volume to another place, it will say that there is no porosity here, so it is minimum here. I mean, it is fluctuating in a larger manner. But when you increase the size to V2, the it is some, I mean, there is some porosity. When you shift this circle to another place, here, suppose here there is having more porosity. See, I mean, at one place it is having more porosity and one other place it is having the less porosity. It should not be like that. It should be the equal porosity. Suppose take here V3. See here V3. Here, when you move this circle from one place to another place, it is having the same porosity. This volume can be represented as the representative elementary volume. It is the smallest volume over which a measurement can be made that will yield a value representative of the whole. I mean, this smallest volume is representing the whole, uh, whole the porosity of your whole region, your study area. That is the representative elementary volume, the assumption behind it. While coming to equivalent porous model, actually, I mean, when you are in deltaic regions, it is totally alluvium area. But when you go to the mountain area, hilly regions, there will be some fractures. I mean, they don't find any alluvial areas. You will find the hard rock regions there in mountain regions. So at that time in hot rock regions there is no porosity. I mean there will be some sort of porosity, but this is primary porosity, naturally occurred porosity. They hilly regions you will be having the secondary porosity, when the fracture porosity or the dissolution porosity, those are the secondary porosity due to weathering or the fractures. Um, that fractured media will represent the uh, 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 interconnectivity between the ports. This type of representation will be carried out. This type of representation will be carried out here. This the same fracture media will we will be assuming it as a interconnectivity between the porous media, granular porous media. So that with that assumption, they have been used this mod flow in the hilly regions also. With this assumption, you need to confirm that when you are doing the groundwater flow modeling in hilly regions, you need to confirm it whether this whether your sample is behaving as the equivalent porous model or not before doing the analysis. Yeah, this is the groundwater governing equation for the flow through porous media. When you are doing about floods, what is the governing equation? The Saint Vincent equation is the governing equation to determine the depth, water surface elevation, velocity, and all. But here in groundwater flow through porous media, the flow through porous media derived by the Darcy is the governing equation here. Here, this is the representative elementary volume which we have been taken, as I explained it before. This is the, I mean, you know the Darcy law. I mean, before you knowing the Darcy law, you need to know the Bernoulli's. While deriving the Bernoulli's equation, you will be considering this thing as pressure coming inside the some sort of pressure P plus dou q dou p by dou x into dx going outside for the small representative elementary volume, that p plus dou p by dou x into dx, where that additional term it came actually. I mean, okay, you can say that mathematically it is represented the change of this element, but when you, that is the physical definition, but when you say mathematically, it came from the Taylor series. I mean, the coming slides I will say about the Taylor series. I mean, just yeah, P plus. I mean, here also there is some amount of flux is entering into the this representative element volume, and the additional change to this dz q plus dou q by dou z into dz. Why we are considering the partial differential equation? Why not the ordinary differential equation? Ordinary differential is like one dimensional, in only one direction we can say, but the partial differential equation we can say in different directions you can represent. That's why only we are using the partial differential equations. In this is the inflow through phase 1. This is the inflow through phase 2. I mean, you know, from that Darcy law you came to know that this formula minus dou h by dou x into d by dz. You plus, I mean, if you subtract, I mean, you know that the mass conservation, the inflow minus outflow is equal to change in the storage in x direction, in y direction, and in z direction. Okay. And W is the volume of the water extracted per unit volume of the soil per unit volume per unit time. And the net flow rate due to the external abstraction is this. I mean, this W represents the whatever the flux. I mean, the recharge, discharge, all these things. This W will represent. If it is minus, it is abstraction. If it is plus, it is recharge into the aquifer. Okay, and change in the storage. This is the specific storage, and dou h by dou t into dx dy. I mean, when you combine this I minus O equal to delta I, then this is the governing equation which you will be using in the mod flow. Mod flow is nothing but modular three-dimensional groundwater flow model. Okay, yeah. For the two-dimensional confined aquifer, the transmissibility will be there because the when you multiply with width of the aquifer, then it is like t k into b. K into b means transmissibility. Uh, kyy into b means transmissibility in the y direction, and it will become ss into b means storativity. Like this it will become when you are considering a three-dimensional thing, yeah, unconfined aquifer thing, then it will be like kxx into h is nothing but the height of the depth of the unsaturated, sorry, saturated from water table to the impervious layer. Yeah, for steady state, we know that for the steady state there will be no change in the volume or the velocity inside the aquifer, so that there is no change in the water table position, whatever the hydraulic head position is no change, and the water table position in the unconfined aquifer also is no change in the steady state, dou h by dou t equal to 0, so that this term will be equal to 0. So this is the governing equation for the steady state, and for the transient state, this is the governing equation. The same thing you can write. That for the transient equation, the water table will be going on changing with respect to time and space for your recharge and discharge. What are the model parameters in steady state used for the calibration of your model? See, when you are dealing with steady state, there is no s, y, s. There are no storage parameters. Only transmissivity parameters are exist here. So you can use only kxx, kyy, kzz for using for uh, um, during calibration. On model parameters in transient state used for the calibration. See, here the SS, KZZ, KYY, KXS, all these terms are used for the calibration in the transient state. Output. What is the final output we are getting? The output is nothing but the hydraulic head distribution with respect to space and time. This is the final output from the mod flow. Yeah, here we need to solve this governing differential equation by using the numerical method. Mod flow is a numerical model, not analytical model. So that's why we are using the finite difference model, finite difference method. These are the different types of methods to solve the partial differential equation by using numerical techniques, but this is the only thing we are using here. F of this is the Taylor series. F of x plus h is equal to f of x plus h by 1 factor of dash. From this only the finite difference method has been derived. Types of finite difference: forward finite difference, central finite difference, and backward finite difference. Forward finite difference means just f of x plus h is equal to minus f of x divided by h, and it is the order is 1 here. The order of the error is 1, but here but here, yeah, in the central difference method, the order of the error is square. Suppose if you are neglecting the one, suppose like 0 point, you know that 0.3 is your error when you are doing the calculation between error between the true value and the your simulated value. So that if you know the 0.3 is the error, then if you substitute here, then there will be more amount of error. But here, if you know that zero point 0.3 is your error, then the 0.3 square is the 0.09. Then the error is very small here in the central difference method. But here the forward difference and backward the error regarding the error, it will be same actually, so that the central finite difference method is the more accurate compared to the forward and backward difference method. 1 minute. Yeah, while after converting, this finite difference method, the main objective of these methods are used to convert this partial differential equation into algebraic equation. That is the only thing behind this method, and the boundary conditions. Okay, before telling this, by using this thing only, your boundary will be You are actually what in while going to finite difference method, you are discretizing your whole domain into subdomains. After that only you are using the finite difference method or finite volume method, whatever finite element method. Yeah, in boundary method, in a boundary conditions, these are the most important. This is also the most important point in the mod flow action. These are the boundary conditions used to solve that algebraic equation within your study area, or within your the domain or the boundary, whatever you are saying. You need to give the boundary condition, so that only uh, it can calculate the hydraulic head variation with respect to time and space within the boundary. Yeah, types of the boundary condition: Dirichlet condition, Newman condition, and the mixed condition. Dirichlet condition means the head is the constant. Newman condition means the flux, dou h by the rate will be the constant. Like mixed condition means the partial, somewhat partial Dirichlet condition and somewhat partial Newman condition. It's a mixed condition. In MODFLOW, there are different types of the packages here: the specific head condition, specified flux condition, head dependent boundary condition. In specified head condition, it is a discrete condition, the constant head. Suppose take the perennial rivers or the seawater surface. It will not change. I mean, in perennial river, the flow will be always continuous. And in the seawater surface, the rise is not in a drastic manner, right? It will be constant. We will be assuming the seawater surface is constant in a model. In specified flux, we are giving some amount of mass entering or some amount of mass pulling out of the system. That is the rate. Um, yeah, recharge package and well package, no flow condition. No flow condition, when you can do the no flow condition means, suppose there is a recharge divide or a discharge divide, a rock outcrop. What is meant by rock outcrop? When the rock came upon the surface, you can see the rock on the ground surface, that is known as a rock outcrop. And subsurface dike. So dike means it is like a wall inside the subsurface. And the head dependent boundary, suppose you can see, I mean, in some areas you can see that groundwater is entering into the stream, or the surface water is entering into the groundwater. When it will happen, when there is a change in the head between the surface water and the groundwater, based upon the head variation only, the river package and lake package and drain package will work. These are the dynamics of the groundwater reservoir. These are the input forcing, the input, recharge from the rainfall, recharge from the canals you should use, and recharge from the surface water irrigation fields. You will be applying some amount of the surface water, some amount of the groundwater into the irrigation fields. From that also there will be a return flow into the groundwater. Recharge from the tanks, ponds, recharge from the water conservation structures, lateral inflow across the boundaries. Suppose if you are modeling for your district, there might be some groundwater inflow in from the outs. I mean, um, the aquifer might be connected with another district, so that you need to um, give the input of the I mean, you need to consider all the things, the another district also, and whatever the thing. Suppose if there is a water movement is from north to south, you need to consider the water coming from the north district and the water going from the south district. It is going in that direction. Suppose it is like that. Under discharge, evapotranspiration, pumping, base flow, lateral outflow across the boundaries, I said, and vertical inter-aquifer outflow. And the vertical inter-aquifer means the leakage aquifer. If there is any leakage aquifer, then there might be some uh, outflow or the inflow, whatever. And the model parameters. These are the model parameters used inside the model. And what we are finding, the hydraulic with respect to space and time, we are finding out from the model. So where we are getting the uncertainty in the model. The uncertainty, the more uncertainty from the conceptualization model. If you need to provide the good boundary condition, good conceptual model, therefore only your groundwater flow model will be perfect. but there might be some due to the recharge, lot of uncertainty due to the recharge and the sync source means recharge and the sync means like pumping, whatever, and the value of the model coefficients and their spatial variation, initial conditions, and the location of the domain boundaries and the conditions prevailing on them, and the degree of the uncertainty is increased in most cases by the lack of the sufficient data. If there is no data, then the degree of the uncertainty will be more. Model misuse, improper conceptualization, or as I said, and selection of an inappropriate code for solving the model. Suppose if your governing equation, if your the boundary conditions are wrong, then the total your model is wrong. Improper model application, misinterpretation of the model. If there is no calibration and validation, then there will be a misinterpretation of your region. Thank you.